Alright, in this video I'm going to be working multivariable calculus homework 1.2. So I'm pretty much going to be mostly taking derivatives and integrals of vector valued functions, but we're going to be doing some other stuff too. First one's talking about this space curve R of t, which is cosine of 3t, sine of 3t, and t. And that's going to make like kind of a helix shape. First, find the absolute value of r, the length of r, and find the length of r prime as well in terms of t. Okay, so I'll start by finding the length of r. And so what that's going to do, I'm going to use that Pythagorean theorem formula. So I'm going to take the cosine squared 3t plus sine squared 3t plus t squared. Then I'm going to also notice that I'm going to end up with a cosine squared plus a sine squared, and that's always 1, so I'm going to have 1 plus t squared inside the square root. And that'll be the length of r, and that's as much as I can do with that. Right, then if you take r prime, you'd get negative 3 sine of 3t and 3 cosine of 3t and 1. And if I went to go take the length of that using the same formula, square root of x component squared plus y component squared plus z component squared, I'd have 9 sine squared 3t plus 9 cosine squared 3t, and I could factor out that 9, you can see there, and I'd still have the plus 1. Okay, so and then that would be the square root of 9 times 1 plus 1, which is the square root of 10. All right, now the next set of questions is all going off this image here. And so I want to show you what how this thing traces out, because this is, like if you're having trouble with it, that's the issue, is that you might need to use some technology to watch this thing trace out. I'm not sure if when I made this problem set I assumed you were going to be using a calculator or what the deal was, but I'm just going to point out first of all that anytime t is 0 or pi or 2 pi, also I think pi over 2 and 3 pi over 2, yeah, all of those places we're going to be at the origin. Okay. So I'm going to say, r is going to equal the 0 vector. I'm going to write down a few times. I can't remember what I said. I may have oversold that, but it's t equals 0, t equals pi, and 2 equals 2 pi. And that makes a lot of sense if you think about, sine of whole numbers of pi is 0. Yeah, that's what we're going to have. Okay, so what that means is that I know what I'll do. Okay, so the curve starts, and I'm going to trace it out in red. And this is t equals 0 increasing towards t equals pi over 2. So we get over here. That's t equals pi over 2. Then it's going to reverse its orientation and turn back around. Probably be a place where the curve was not smooth. And that's going all the way back around here, and I'm approaching t equals pi. And that's t equals pi, right? Okay, and then, as t increases from pi towards 3 pi over 2, I'm going to be down here. And this will be t equals 3 pi over 2. And then from t equals 3 pi over 2 to 2 pi, it will trace back all the way towards the origin. Like that. Okay. All right, so that's like to give you an idea of the orientation of the curve. So what I'm saying is that the point P, its t coordinate, the t coordinates between pi and 2 pi, right? Because it traced out that thing that you can see in blue right now first, and then it went back on itself. Then it went down into the third quadrant and swooped around. Okay, so there's actually going to be two different t coordinates between pi and 2 pi that work, one in kind of each quadrant. So I'm going to say I'm going to be searching for the one that's between pi and 3 pi over 2. Okay? Now the thing that is interesting about point P is that its x-coordinate is 0. Okay? So that means I'm looking for 3 sine of 5t to equal 0 on the interval pi to 3 pi over 2. There should only be one solution to that. So, sine of 5t equals 0. Well, sine equals 0. Bring out a quick circle. Here and there, okay, at 0 and pi, but also 2 pi, 3 pi, 4 pi, 5 pi. Okay, we know it's between pi and 2 pi, so we might pick up at 5 pi over 5. Okay, so 5t equals, pardon me, 5 pi, 6 pi, 7 pi. Now, I'm not going to go all the way to 8 pi because that would be, when I divide it by 5, 8 over 5 is bigger than 1.5. Yes, that's right. Actually, I better change part. I'm going to be a little bit more detailed here because this is actually a much tougher problem than I'd given it credit for. Maybe I just didn't realize this was a hard problem and I've been on my homework for a few years. And I thought I'd had a video for this one. Either way, t equals 5 pi over 5. That's pi, 6 pi over 5, 7 pi over 5, 8 pi over 5, 9 pi over 5, and 10 pi over 5, which is going to be 2 pi. Okay, now I am going to actually maybe label those. Maybe I'll use a highlighter. So starting at pi, which is where we're at the origin, okay, that's the first time x is equal to 0. Then it's 6 pi over 5. That's the second time we hit x equaling 0. So 7 pi over 5, that's the one I'm really interested in. I'm going to get a special color for that. Yeah. When I hit point P, that's going to be 7 pi over 5. And I do believe that it's, oh yeah, okay, because 3 pi over 2 would be between 7 pi over 5 and 8 pi over 5. It's 7.5 pi over 5. Okay, that means that 8 pi over 5 is also a t-coordinate of point P. Then 9 pi over 5 is a yellow highlighter spot. I'm going to do that, and I'm going to get the yellow highlighter away from the origin because I don't really even need that. T equals pi and 2 pi, it's at the origin. I already told you that. Okay, so I have found the t-coordinate of point P. I'm going to use t equals 7 pi over 5. Okay, so the y-coordinate of point P is going to be y equals 3 sine of 7 pi times 3 is 21 pi over 5. Okay, and that's going to be an exact value. I'm sure that you could figure that out somehow. I don't really know how you get to pi's over 5 with trigonometry, but I'm not that advanced of a geometer. So I'm just going to stop there. That's an exact value. That's good enough for me. All right, so now we're going to find the x-coordinate of point Q. And so I think, because it's on that first part of the curve, on that blue portion, I'm going to say t-coordinate of Q is between 0 and pi. And actually, I can say I'm just going to find the first one between 0 and pi over 2 to save myself a little bit of effort compared to that last part. Okay, then the most interesting thing about Q is that its y-coordinate is equal to 0. So that means that 3 sine of 3t needs to equal 0. And once again, sine of a thing is equal to 0 when that thing is, some whole number of pi. So that's going to be 3t equaling 0, 1 pi, 2 pi. Okay, but even still, I think that's gone too far because when I divide 2 pi by 3, that's bigger than pi over 2. So I'm going to get that one out of there. T equals 0 is also out of there because at t equals 0, the curve's at the origin. So I know that the t-coordinate of Q is pi over 3. Then the x-coordinate is going to be 3 sine of 5t, so that's 5 pi over 3. We can figure that out. Might have been a while for you, but we can do that. 5 pi over 3 is down there. It's almost all the way to 2 pi. It's just short by pi over 3, which is kind of like 60 degrees. And so I'm going to say, all right, draw my triangle. My reference triangle always has a hypotenuse 1. This is exactly what we're doing in my pre-calc class right now. The short leg is a half, and the long leg is going to be root 3 over 2. Now we're in the fourth quadrant, so this needs to be negative. And so 3 times the sine, SOHCAHTOA, opposite over hypotenuse, that's negative root 3 over 2. So that'll be negative 3 square root of 3 all divided by 2. That's the x-coordinate of point Q. Next, we're going to find the slope of the curve. And that's something that, I'll be honest, I was more interested in that. That's kind of AP calculus. I was more interested in that when I wrote this homework than I am now. And so I'm more interested in the vector valued function part of this discussion. And so this is probably not a question I would be asking anymore. But dy dx, that's going to equal y prime over x prime. It's still a valid question. You'll have to ask me, is that going to be on the test this year? Because year to year, I'm not going to necessarily be able to say. So y prime over x prime, and so I'm going to need to take those. So r prime of t is going to equal 15 cosine of 5t and 9 cosine of 3t. Okay, at t equals 1, well, that's interesting. And dy dx at t equals 1 will be the y coordinate of r prime at t equals 1, which is 9 cosine of 3, divided by the x coordinate at t equals 1, which is 15 times the cosine of 5. And I'm not doing these problems with the calculator, so I'm going to just be stopping there. But I think the real test is going to be number 6 when I have to go find the length of the curve. I think I'm not going to have a good chance of being able to compute that because the arguments of and I wouldn't have a sine squared plus a cosine squared. I don't know what's going to happen there. We'll find out. Number 5 is asking if the curve is concave up and concave down, and I would rate that as another one that I was probably more interested in when I wrote this homework than I am now. That's something we have to do in Cal BC, but not applicable to a space curve, and that's what I care about more now. And I'll just remind you the formula for the second derivative of y with respect to x that you can use to determine if the curve is concave up or concave down. I could probably also do this by just looking at the curve. I think pi over 3 is most of the way to pi over 2. And so I would say it's gotta be concave up, right? Because it looks like I don't know about it first. It might be concave up, but then it's concave down for a long way. And then it resumes being concave up again at some point. Anyway, t equals pi over 3. Derivative with respect to t of dy dx. Ooh, that's going to be annoying. Honestly, did not think that would be the straw that broke the camel's back, but I consider it broken, and I'm going to go over here and say I'm going to do this one with a calculator because that was going to be really brutal on the derivative taking front, because I was going to have to take the derivative of 9 cosine of 3t divided by 15 cosine of 5t, which would have had quotient, chain all over the place, having to keep track of stuff, then plug in the pi over 3 and do all the unit circle trig. Yeah, we don't have time for that, right? What we're going to do is we're going to say, and do you think I am going to plug these into y1 and y2 though? So x prime is going to be y1, 15 cosine 5t. Then y2 is going to be, y prime of t, 9 cosine 3t. Alright, then we're going to call for a fraction. So if I want the derivative, that's math 8. The derivative of another fraction, y prime over x prime. That's going to be, that's a matrix. It's over here, yeah. prime was in y2, x prime was in y1, point where the input is pi over 3, and then we're going to divide by dx dt at pi over 3, so I will call again for y1 and plug in pi divided by 3. See, that was a lot just to even type in. And that should give me a value that's positive, concave up. That's what I expected to happen in the first place. So that basically, tablet screen went out. Been idle for that long. Okay, this number right there, evaluated at t equals pi over 3, gave me that number. It's in the calculator, so I'm going to conclude concave up and leave that problem behind. But I might not be done with the calculator. Talking about the length of the curve, again I erased r prime. So r prime is going to be, I'm just going to write it as a vector, like its coordinates 15 cosine 5t and 9 cosine 3t. All right, so the length of the curve is going to be the integral from 0 to 2 pi of the square root of x prime squared, 15 squared is 225, cosine squared 5t, plus y prime squared is 81, cosine squared 3t. Yeah, that's not, I don't know anything I can do with that algebraically. I don't have a formula for like sum of two squares, or then I can like factor there, do trig identities on. So that must mean I'm going to be calling for math 9 from 0 up to 2 pi. That's going to be a pretty big square root. 225 cosine of 5t squared plus 81 cosine of 3t squared with respect to t. Let's think for a while, I bet. A lot of numbers trending around in there. It's taking a little long. I think, is there, no, there's no way that would come back negative. Just squared the cosines. Well, you know how those total distance integrals are. Yeah, they take a while to run. So it's going to be 73.732. Okay, I suppose that's believable. I mean, it traced out that whole curve twice. I mean, I don't know. I don't feel like I necessarily have a good scale for what total distance looks like on a graph. All right, and the position of those problems 7 and 8, I feel like this wanted to be number 1 and 2, or like 2 and 3, like the first two. I'm really not sure what's going on here. This is a weird problem set. We've already done that. We've labeled the points that correspond to t equals 0 and t equals pi. We've found r prime of t many times. So I'm just going to move on to 9. If r represents the velocity of an object moving in the plane, okay, so r is the velocity. What we're going to need to do is, say, position 1, so 0 and 4, plus the integral of velocity. Okay, and the velocity is r. Would think that r would represent the position, but evidently not. And then, oh wait, no, at time t equals 0, and we're going to time t equals pi. All right, now this is something I probably will be able to do by hand. Now the integral of r of t is just going to be integrating 3 sine of 5t and 3 sine of 3t. I'm wondering if this is going to come back with no change in position, but it'll be all right. All right, so the change in x is going to equal the integral from 0 to pi of 3 sine of 5t dt, which is going to equal negative 3/5 of the cosine of 5t as t runs from 0 to pi. Oh no, this is going to have some distance. So that's equal to negative 3/5 times cosine of 5 pi would be negative 1, cosine of 1 of 0 is 1. So I've got negative 2 times negative 3/5 is going to be positive 6 over 5. Okay? That means I'm going to have my change in x was 6 over 5, so there we go. Now I'm going to need to clear that out and find the change in y. Change in y is going to equal the integral from 0 to pi of 3 sine of 3t. I wonder if this is going to work out the same, except it's going to be 3/3 instead. So, let's take it all the way through. So I'm going to anti-differentiate. I would get negative 1 cosine of 3t as t ran from 0 to pi, which is going to be the negative of cosine of 3 pi is negative 1 minus cosine of 0 is positive 1. Yep, that's going to be... Is that the right thing? Yeah, I'm just going to take that on faith. I hope that was. Because I just got positive 2 there, and 4 plus 2 is 6. Yeah, okay, maybe. Oof, I don't feel great about that x coordinate, but I'm just going to move on. Oh, well, I guess I could have known that there was going to be a calculator if I had seen that it was find the area of the surface. Okay, so r equals t squared and 16 minus t to the 4th from 0 to 2 around the x-axis. We don't even really need to sketch the thing, because I don't know, that's probably not what it looks like. But if it is, and we're rotating around the x-axis, the radius is the y-coordinate. It's the integral of 2 pi RL. And r is going to equal the y-coordinate. And we are going to integrate from 0 to 2 because those are the t-coordinates. 2 pi times the y-coordinate, 16 minus t to the 4th, times the square root of x prime squared, so that would be 2t squared is 4t to the 4, plus y prime squared, negative 4t cubed. I would square that and get 16t to the 6 with respect to time. It's definitely a job for the graphing calculator. I mean, I could factor out the 4t to the 4 from both of them. That would help. But then I'd still have 1 plus 4t squared. Now, I will say that I do think that this one is like one that you could possibly integrate by hand, because I know there's a lot of integrals that have like the pattern square root of 1 plus something squared. And those are the ones you can look up in the tables. Yeah, they're like out there. It used to be in the back of the book when you had a textbook. But you could, look up tables of integrals. Sometimes those integrals come up in physics. Not because I've taken a bunch of physics classes, just because I've had physics students come and ask me before. But this is one we're going to compute with a calculator. So we're going to go math 9. From 0 up to 2 of 2 pi. R was 16 minus t to the 4. Then we multiplied by our small piece of arc length, which is the square root of 4t to the power of 4. What is going on? There we go. Plus 16t to the power of 3. No, that wasn't a 3. Oh, that could have been bad. Giving me totally the wrong answer. I'm just 2 pi RL. Also has the dt in it. That that one was quick by comparison, 866.215. Okay, and find the area of the surface generated by rotating this thing around the y-axis. Okay, so I'm assuming it's going to kind of look like that if it's going to make any sort of an interesting looking surface. So the radius is going to be the x-coordinate. Zero to 2 pi x-coordinate, 2 plus cosine pi t. And then, oh man. And I'm going to take the derivative, and so that would be pi squared sine squared pi t. What was I thinking? This one, we're going to write it and not evaluate it. Because I know you can operate Math 9 on a graphing calculator, and I don't think, God, plus 4. Okay, at least that one was easy. I took the derivative of 2t plus 3, got 2, squared it, and that's 4. Yeah, and then add a dt. That's going to be it. That's the bottom of the homework. That was an interesting problem set. I gotta say, I don't think I'm gonna look at the quiz real quick. Yeah, it's closer to the notes. But I still like these problems. I thought they were interesting and they're definitely challenging, especially that curve. That one really threw me for a loop. But that's gonna be all for this video. Thanks for watching.